Dear students, let's proceed with our lectures, and it concerns with uh, attention processes in RC circuit. At first, it will be at connection to a DC source. So it was in previous lecture, but please listen it attentively, because we will need it further, and I think that it is not a bad thing to listen it one more time. Okay, so we have RC branch which was disconnected from any source, and it was no closed path for flowing current through this branch. But after commutation, after this key is closed, DC source, namely this E, you see it's capital letter, so DC source will be connected to this RC circuit. So before switching at t less than 0, this capacitor was not charged and was disconnected from it. It was not closed path, so you see 0 was equal to 0 and IC 0 was equal to 0. So condition UC from minus 0 equal to 0 it should be fulfilled. Let's consider case time period when t is greater than 0. It includes, I would like to remind you, such a time period includes both period of transient change of currents and voltages in the schematic, and steady state processes when transient processes is over. And for this, it is necessary for us to write down equation which depict electrical processes in such a case. It's sum. We can write down that sum of voltage drop across resistance plus voltage drop across capacitance equal to this EMF. With help, we write down this equation with help of second Kirchhoff's law. You see, it is C duc by dt, it's IC, this current, and when we multiply it by R, we've got voltage drop across resistance. Solution of such an equation equal to sum of forced component and natural component. So, when applied EMF is constant, when it is DC, possess DC character, UC forced also will be constant, and IC forced equal to C duc forced by dt will be equal to 0, because if we have constant UC forced, derivative from any constant volume equal to 0. Okay, you should remember that DC current in steady state regime does not flow through capacitance. It's something like a brake. It's even may be seen from this drawing, from this picture, from this graph. From this schematic. So we can write down that UC natural equal to A e to the minus T over tau C, as was explained previously, and tau C, time constant, equal to product of R and C. Let's use second switching law for determination of this integration constant A. We can write down UC for t greater than 0. It will be equal to this AE plus it will be forced component, and this is A multiplied by e to the minus T over tau C, its natural component. Why UC force equal to 0? Why? You see, in steady state regime, it will not be any current in this circuit, okay? So it will be it will not be voltage drop across this resistance. So all this EMF E will be applied to this capacitance. So we can write down that UC force equal to this EMF. It is here. Okay, so we write down this expression for voltage drop across capacitance instead at t greater than 0, and as you see from minus 0 equal to 0, and you see from 0 plus equal to this expression at t equal to 0. It will be this EMF plus A multiplied by 1, because exponential function in 0 degree equal to 1, 2 unit. So from here we can write down that A equal to minus E, because E plus A equal E plus A, you see from plus 0 equal to 0, for you see from minus 0. From here A equal to minus E, and we can write down that you see equal to this EMF minus, because A equal to minus, E, because it's in module equal to E, multiplied by exponential function of minus t over tau c. And we can calculate also IC current which flows through inductance, and in our case the same current will flow through resistance. It will be C duc by dt, okay? C, then it will be you see derivative by time from this expression. From the first item it will give us 0 because it is constant, and derivative from second item it will be minus, because it is before this expression, E multiplied by exponential function minus t over RC, and it should be multiplied also by derivative from the argument. It will be minus 1 over tau c, or 1 over RC. Okay, here C and C are cancelled, and we will have minus and minus will give us plus, and we will have here E over R, okay, multiplied by exponential function of minus t over RC. Then we can depict graphs of these functions, both of UC and IC. Before commutation, as concerned UC, before commutation, UC was equal to 0, and after commutation in steady state processes it will be equal to UC force, and it will be equal to this EMF. And before these two states we have tension processes which refers to exponential function, and duration of this tension process is approximately equal to 4.6 tau c, where tau c equal to R multiplied by C. You see it is we have here UC forced, its constant EMF, and here UC natural equal to minus E multiplied by exponential function from minus t over tau c. You see, so it is at the first moment it was minus E, then it changed in accordance with exponential function. When we sum up this natural, UC natural, and this UC forced, we have this exponential function UC, okay? And we can see that at the first moment t equal to 0, this value retains its 0 value as it was before commutation. It will be the same at the moment just after commutation. And as concerned IC, you see, for the first, you can see that it consists only of transient component, and it will be equal to tends to 0 when t tends to infinity. 0 value, and before commutation this IC current was equal to 0 also, because this schematic, this RC circuit was disconnected from the source before commutation. So we have here 0 level before commutation, 0 level will be at t tends to infinity, and before these two states we have tension processes, and at the first moment after commutation we have sharp change in level of IC. At the first moment, you can see at t equal to 0, we have had a value of IC equal to E over R. Okay, so it was from 0 to E over R, and then again it was changed up to 0 level. Why it is possible and why it occurs when current IC change so steeply at the first moment after commutation? Because it is dependent initial condition, and such dependent initial condition can change steeply, can change immediately its value immediately from one value to just another. Why? Because just this change provide smooth changing of UC or voltage drop across capacitance, because voltage drop across capacitance can change only smoothly, because otherwise it will be we will require infinitely big influx of energy to provide steep change of voltage drop across capacitance, and this smooth change such smooth change is possible just due to sharp change in current of through this inductance. You see, now we will finish this part of lecture, and next part will deal with turning on RC circuit, RC branch to AC EMF, to alternating current, alternating voltage, and we will see in such a case you should remember that it will be current through inductance in steady state regime, because we will not have here DC, we will not have here steady state constant voltages and currents. Derivative will not be equal to 0, so we will have current through inductance. Let's proceed in the next lecture. Bye bye for now.